we'll just start going through the last couple of sections in chapter 17, which is from the two sections on progressive growing of GANs and style GANs. So it's only a few pages, and since the pages are so few, we can spend more time in the notebook going over that corresponding part. So let's go ahead and start, and I think it'll only be like half an hour's worth of reading, and then we can meet at, well, let's say 7:10. We'll meet at 7:10. I forgot to check if everybody can hear. Can everybody hear what I'm saying?
Mm-hmm.
Yes.
Yes, no? Huh, I
Yep.
can't hear you.
Yes, we can hear you.
I'm gonna make sure my system is working. Oh, let's see. Well, according to my, so nobody can hear? Oh, you can't hear, but how come I can't hear you? Can somebody say something? I can't hear you.
Mm-hmm. Can you
Oh,
hear me?
there's Mayank. Can you say something, Mayank?
Yeah, I'm speaking.
Oh,
I don't think
I
so. You
can't hear
can.
you.
Yeah.
Never mind. That's fine. We can still go ahead and start reading, and I'll sort this out later. Let's meet at 7:10, and we'll begin our discussion. All right, we're back. So how did that go? I still got this problem with my. Let's see. Let me just see if you guys can hear me.
Yes, we can hear you.
Oh, good. Now I can hear you too. So I think things are working. Programs. Oh, somebody put a. So Maya put a reference out here that explains progressive growing of GANs. Oh yeah, that's the one that's referred to in the book. Yeah, so there are two references. There's the reference 16, footnote 16 and footnote 18. So there's two papers. And if you, let's see, how come I just lost what I had? And then there's also a reference to a YouTube video, Progressive Growing of GANs. We should probably look at that YouTube video first, just because it's short and gives you an idea of what GANs can do. So I'm gonna play that. Can you see that right now, the video queued up? Yes, no?
Joseph, you're not sharing anything, I think.
Okay, thank you. It's always good to make sure you're sharing first. Hold on. Okay, here we go. Share screen 2. Okay, now what are you seeing in the shared area?
Yes, we can see your browser.
Okay, can you see the YouTube video queued up?
Yes.
Great. Okay, I'm gonna full screen that and then play it. Let's see. I forgot. I have to take off my. Let's see. I have to take off the headphones. Let's see. Turn on. Let's see. If I. Hold on.
Joseph, we are not able to hear you.
Okay, can you hear me again?
Yes.
Okay, great. We're back in business. Okay, so anyway, that I thought that video was kind of scary, actually. It just looks really eerie. But the point is that you can produce images of celebrity-like figures that are very convincing, and in some sense you don't really need beautiful models anymore, because you can just synthesize those images with these GANs. Okay, so the first thing is this. There's two things. There's two sections. One is the progressive growing of GANs, where they. I'm not quite sure I understand this whole thing yet, but they start with a small image, then they like say a 4x4 with 512 filters, and then they apply a convolution that seems to leave it with 512 filters, and then another convolution that leaves it with 3 filters, so it's RGB. So that transforms it into an RGB. And then they, I guess they take that, I guess they take this, I'm not sure what they're doing from here to here, but so this is a similar architecture, except that instead of just going directly to the 4x4x3, they first upsample it to an 8x8 by 512. You know, there was the same number of filters, but they upsample the number of pixels to 8x8. And then they branch, okay, in one branch, the 8x8 gets mapped up to a 8x8 RGB image. And in the other branch, it goes through a convolutional network and gets mapped to down to 256 filters, and another convolutional layer that maps it to an RGB image. And then they combine these linear combination of these two outputs. And then he says they adjust to the outputs so that alpha starts at close to 0 and then ends up close to 1, so that you're mostly using, so that at the end you're using this branch, this branch. And it has something to do, according to the text, with not breaking the upsampling thing, because if you just went, I guess, straight up to the 8x8x3 by this branch, something bad happens, I guess. So instead, you tweak this alpha. You start out with alpha close to 0, and then you start with small values, and then you keep adjusting it and adjusting it until you get up to 1, and then that's your final output. So eventually, the path is this way. And that's all I've managed to understand about this. If somebody has a deeper insight, please jump in.
Yep. This text explains all of these three things: the mini batch, the equalized learning rate, and the pixel-wise normalization there. I would just recommend you to open up the presentation and that
Yeah.
the link that I've shared.
Yeah. Let's see. I
It
had
has.
it
Yeah.
open. Let's see. Is this the one? This is not. So if I here, I think I overwrote it. Let me get it back.
Yes, the progress.
I had it open. Yeah, I had it
Yeah.
open.
It's the second link.
The second, not this one,
The
but
second tab. The tab that you have opened.
oh, second tab. Yeah, this one. Yeah, this is the code, right? But there's a paper.
Yeah. If you go down, I think so. There's a presentation too. Yeah.
Is this it?
Yeah. The second link in the top, from the top.
Second link from the top is here. Yeah, okay. I had this open before, but then when I clicked on your link, it overwrote it or something. So I'm going to open this, and then I'm going to.
There's a PPTX file.
Open it in,
Yeah.
I'm going to open it in PDF. Okay, so this is that paper, right?
Yeah,
and it's it's 26 pages, but it's really not. It's only about 10 pages of text. The rest of it is images and stuff. So shall we just go through?
I was referring to the presentation. There's a PPTX file to it too.
Oh, okay. In this paper, there's a
PPTX file. Yeah.
A PowerPoint. Oh, back. You mean back in the paper? Is that linked to?
Yes. Okay. ICLR 2018 slides.
Okay.
In the same page that you had opened.
Yeah.
On the GitHub.
Back to the GitHub. Okay. Where is it? That's not it. There it is. Nope, that's not the right one. Oh, I think it detached. There it is. So there's a PowerPoint slides from here. Is that what
Yeah,
you're saying?
and
Yeah.
they have explained it beautifully there.
This one.
Yeah.
Okay, got it.
No, no, it's from, yeah, this one, yeah.
Oops, it says doesn't
It's
exist.
300 MBs of stuff. Yeah,
So wait a minute. It's the ICLR 2018
yeah,
slides. Is that it?
yes,
Okay, and I
you're right,
clicked on that,
intelligence.
and then it says that it doesn't exist. So let me see.
And,
Let's see. Get stuff done. Sorry, the file you requested does not exist. So
I will share you the
you
link.
got it.
Yeah,
We'll try it. Copy link location. Let me just try this one more time. Nope, it doesn't have it. Okay, so you're sharing it in the
yeah.
chat.
Is this the same? If you
Uh,
click on the chat,
Okay, in the chat. Chat. There it is. I click on that link. Yeah, it says that it doesn't exist.
Okay.
Maybe if we Google for that particular paper,
personal.
yeah, this must be it. This is these guys, right? Karras, Karras. Yeah, this is it right here, I think. So, oh, but it's slides. So if I do this, and then just let's go through these slides. Can everybody see that?
Yes. Yep.
Slides. Okay, so let's just go through. So, okay, motivation. Generate image. Sharp, blurry, sharp. GANs are sharp. VIEs, we already saw, are blurry. Variational autoencoders are blurry. Autoaggressive, we didn't really look at these, but information bottleneck, disadvantage. Only work on small resolutions and hard to train. Okay, so that's why is it hard? Higher resolution is easier to tell difference. Okay, smaller batch size. Smaller batch size because you have larger images, is that it? Or higher resolution means that the image is bigger, so you need smaller batch size. Okay, so grow G and D, generator and discriminator progressively. Okay. So 4x4. Latent. Okay, so here's the encodings. The generator generates the encodings. The discriminator takes real images and decides whether that's a real image or not. It takes the generated image, compares it with reals, and decides whether this is, and classifies it as real or not. Then the generator takes encodings, scales them up, and compares that against a real image. I guess this is still the decoder part here. Now this resolution is 4x4. This resolution is 8x8. Then it maps it back to 4x4. I guess I'm not sure why. And then you just have many of these layers, and then finally you get up to where a full scale 1024 by 1024 image. In which case you can now compare that with real 1024 by 1024 images, and so you've okay, so now you've trained a network to be able to create and distinguish between, to generate 1024 by 1024 images, and also to be able to tell whether discriminate real and fake images. And then let's see, I'm not quite sure why it maps it back down to 4x4 after the discrimination gets done. but it seems to be constant, that it always maps it back to 4x4 in each one of these steps. So that's okay. So let's keep going.
Isn't the discriminator's job to kind of tell you true or false? So you come back to 4x4, and then you'll still have, I think, like normal multi-layer perceptron there, which basically gives you an output 0 or 1, right? Whether it's real or not real.
Sorry, I didn't get the last thing you said.
So finally, at the end of the day, it should tell you whether it's real or not real, right? The discriminator's job is to just tell you whether true or false.
Yeah, so that gets done here, right?
No, right? There, you still pass in both the images at whatever resolution. 1024 by 1024, that will pass through the decoder or the discriminator here. So it starts from a 1024 by 1024 resolution and then funnels down. And it funnels down here to like a 4x4, but then it will still continue down to something like a 1x1, where you'll basically have a sigmoid at the end, which should tell you whether it's real or not real, right?
Okay.
At least that's what my
But
understanding.
why doesn't it just go from 8x8 directly to a one pixel?
You don't want to do that because that's the whole thing with the progressive growing generator, right? You're stacking on 4x4 to 8x8, and then you keep increasing by that 16x16, and then so your each of these layers is still present in your final network. That's why on the rightmost diagram, it's not like you're just giving it a latent vector and you're directly going to 1024 by 1024. You're progressively building 4x4. You still have all those convolutional layers which are present.
So
Initially.
so the discriminator doesn't do anything until the very end. Is that what you're saying?
I don't think so. Each step, both the G and D work together, right?
Yeah, so that's what I'm thinking is right here. Okay, so this step, the discriminator compares with a real image, and then there's a 4x4, which I would presume it maps down to 1 pixel so that it can make its decision, right?
Right.
And then here, it compares 8x8 images, and then I'm not sure why it doesn't just map this directly down to 1 pixel to make its to make its decision. Why does it go to 4x4 first and then to 1x1? I mean, it doesn't even show that it goes to 1x1, but you presume it does. Yeah, so I'm just a little bit puzzled by the, and I can see how this extends. The next level would be, 16x16, and it would have 4x4, 8x8, 16x16 here, and so on. And so you can see there's a continuous progression from this architecture to this architecture. But I'm just not quite sure how it works. Okay, so fine. This is the next page. Okay, so 16 by, wait, did I miss something? That's that, and then that's that. Okay, so generator starts with a 16x16 and creates 3 channels RGB. Then the discriminator starts with the RGB, funnels it back down to 16x16, and then I'm not sure what. Then this is that little extra bit where it has 2 channels that get added together, 2 paths, I should say, that get added together. So you upsampled at 32x32 and then to RGB. And then in a parallel branch, you add a linear combination of these 2 branches. And what it doesn't show is that there are extra convolutional layers on this side. You end up, both of these branches end up with 32x32 RGB. But on this side, there are a couple of extra convolutional layers. It's at least according to the text. And then you add a linear combination of them. And then you keep doing this by linearly increasing alpha from, you start with 0, in which case, it's all of this branch. If it's 0, then it's all this branch. And then when you increase it to 1, then it becomes all the right-hand branch. And then this is just the reverse, I guess. Okay, so this was scaling it up, and this is scale, from 16 by 16 to 32 by 32, and then this one scales it the other direction from 32 by 32 back down to 16 by 16.
So in this example, the convolution is not on the branch to the left, right? They're all.
I think it's the other side. Yeah, I think
Right.
it's to the other side, the way it's, yeah, the book. Yeah, I'm just remembering the picture from the book. And,
Yeah,
but
right.
yeah, the convolutional layers on this, the 2 convolutional layers are on this side.
So you upsample by 2x, you go from 16 by 16 to 32 by 32.
And then you downsample.
Right. So when you have alpha is equal to 0, all you're doing is basically saying, give me just the upsampled version. So in the upsampling, you're not really learning anything, right? There's no convolutions in that.
Wait, aren't both sides upsampled?
Right. So I'm saying when you do 2x, you get 32 by 32, which is split into 2 branches. 132 by 32 basically just comes in. That's the 1 minus alpha.
Yeah,
So,
it's kind of like a skip connection.
Yeah, I'm not sure if that. Okay, I'm not sure if that is a skip
like an
connection.
identity. It's like an identity connection, right? Because nothing's done to it.
Right, but in the initial phase you want to use that is because your conv layers on the other side, that's on the right hand side, haven't really learned anything because it's the first pass. So that's why their alpha is 0. So as you learn, you keep reducing just the upsampled version, and you start believing more and more of the convolved upsampled version.
Oh, I see. That makes sense. So you start with just the raw upsampled version, which is probably going to be pretty, which isn't going to be very good.
Yeah, something like nearest neighbor, let's say. So it's not going to be that good.
Yeah, and then you gradually start learning the 2 convolution networks that help to put in more detail into the image. Yeah, thanks for that insight. That's a really great insight. I think that really helps to put it in context. Yeah. And then not sure what this side is.
So actually, all the 3 diagrams that you're seeing is the same thing. It's just alpha progressing from 0 on A, alpha somewhere in between.
Okay. I see what you're saying.
Yeah.
I see. Yeah, that's right. So this is alpha equals 0, which just includes the upsampled image. This is somewhere in between where there's an alpha between 0 and 1, and you're having a linear combination of the 2 branches. And then finally you reach alpha equals 1, and then you're just taking the right-hand branch, and that's what this is. Yeah. Okay.
Yeah, just to add, here is the linear crossfade. That's the plus sign with a circle. That's the concatenation. That's called the linear crossfade, and that's in the paper too.
So you're just linearly, you're just increasing alpha along a linear grid, starting at 0 and ending at 1.
Then adding it, yeah.
And then when you're done, you're here.
Yeah.
As Rachel told us. Yeah. Okay, great. Let's move.
So that's not concatenation, right? It's just.
It's not concatenation. No,
right.
It's
not concatenation. Yeah.
Okay, mini batch. This is the second tweak on this method. Insert a constant feature map, compute standard deviation, and concatenate with the. Okay, so you start with a constant feature map, just a bunch of a pixel array with a constant in it. If it's constant, then how does it have a standard deviation? Compute standard deviation and concatenate. I'm not sure what that means. Equalize learning rate using her initialization. I think he said something about you use the her initialization, but only, let's see, only at runtime or something like that. That's what he said. Maybe it talks about it more after every conv layer in the generator. It's like batch norm, but works pixel wise. summing over the AXY J squareds. AXY is the feature map, I guess, the coordinates of the pixels in the feature map. J is filter layer, or I'm not sure what, you're summing over the filters maybe, and N is the number of, N is the number of, yeah, so N is the number of filters, the number of feature maps. And so you're summing at any one pixel, you're summing across you're taking the pixel value and normalizing it by this thing, which goes across the feature maps. So if I draw a picture of it, it would be kind of like this. So let's imagine we have a bunch of feature maps sitting there. Let's say we have 3 feature maps. And then we take a pixel in here, let's say the 2 pixel, and it's maybe right here, okay? And you get the 2 filter, the 2 pixel here, and the 2 pixel here. So this is filter 1, filter 2, and filter 3. And then this is, and so, you know, it goes up to N, right? Right, there are capital N filters, and each filter is, you know, let's say it's M by, you know, M by N, something like that. So we have 3 filters, and let's suppose that we only have 3 filters. Then what we're doing is we're taking every, oh, now I'm a little confused, because AXY refers to a particular pixel where, you know, X is the, I suppose the column number, and Y is the row number, and that gets you to a pixel. I think, no, you're summing over. I think that this should be, this should have an index on it that tells you which filter you're talking about. Because what you're doing is you're taking these 3 pixels and doing this. You're taking the sum of the squares, and then you're adding this this extra term for stability. But it's basically the average squared pixel value, and that's what's being used to normalize every. So suppose I'm on filter 1, and then I have this pixel would be called AXY. Then he's producing this BXY. AXY is getting mapped into BXY by simply dividing it by this normalization factor. And the normalization factor is made up of these 3 pixel values that are the same. You know, in other words, the AXY, let's say AXY, let's label these filters 1, 2, 3, then A1XY, I think, is going to be this value, but then B1XY is going to be this value normalized by, you know, by this denominator. And then you have to do the same, it seems to me, you have to do the same thing with A2XY. You know, you can refer to a point on the second filter. And here I don't mean A squared, I mean, you know, A2 as an index. Filter number 2.
X and Y, like you said, is just height and width, right?
Yeah, X and Y is just height and width.
Right. So if you index X and Y, you'll actually get back a vector back, right? Which will be of height 1, width 1, depth n, where n is the number of channels. So B X comma Y is basically 1 by 1 by n.
Okay, yeah, you could think of it that way. Then this thing, if you consider this as a vector, that's what you're saying, right? And the vector consists of all of these pixels.
Right.
Okay, that makes sense. Then that's the same thing as I was getting at here. But the point is that this vector consists of these 3 values. So what you're saying is that the AXY is really meant to be, you know, A1 XY, AXY on filter 1. It's like a vector. That's AXY on filter 1, AXY on filter 2.
Yeah.
Yeah, that makes good sense. And then, sorry, but this is really slow. And then AXY on filter 3. Okay, so sorry about that. So we have this vector, and then we map it to this new vector called BXY. And to do the mapping, all we're doing is normalizing each term by this thing, which is a constant. We're dividing each of these terms by this constant, which is the sum of the component, the sum of the squares of the components of that vector. Does that make sense?
Yep.
So you're sort of normalizing by the scatter in that vector, normalizing by the standard deviation in that vector. Yeah. So it's kind of like a standardization, similar to what goes on in the standardization step, where you divide by the standard deviation. That's what this really is. It's the standard deviation in the pixel value across the filters.
Yeah.
Okay. All right, then let's move on.
Just to share an image.
Yeah.
Yeah. Maybe I will share this at the end first, because the presentation that I shared the link with you, it had a great intuitive representation with the images which are presented side by side. So there
Did you
you,
just is this it here that you shared this link in the chat?
yeah, it's the same, but
Okay,
it's not
let me click on
opening up.
that. Oh, it's not opening up. That's right.
Yeah.
Yeah, that's the problem.
Okay,
So
then please
do you
go
want to
on.
share?
Yeah.
You want to share your screen or something, or?
Yep, I would
Oh,
love to.
okay, I'll let go of my share and you can do it.
Okay. So if
Yeah.
you guys can see my
Yes.
screen here,
Yep.
that's what I was referring to here. So let's go over from the top. They have given a comparison, and then this simply how to generate samples, simple formulation of the loss of the generator, which is the negative of the dx of this. And here they are trying to simply set the expectations, which is sampled from the probability of G, and then this minus this guy here. And see the here, if you can see my cursor, this is the king of waves, the Aquaman, I suppose. And this energy, this expectation refers to this guy here. And then if we have to reach here, that's the discriminator, the expectation of this guy towards this treasure chest. And this is the lambda multiplied by the expectation over the squared of the gradient of x hat, which is the which is mapped to the L2 norm here with the discriminator of x hat, and then that's the whole term here that we are trying to. That's the cost function of our uh, this guy discriminator, and the lambda here is the step size, and we have to reach here. This is what
What
the
is
energy.
the function D?
D is the discriminator here. If I see from the paper, what they have referred to here is the layers that corresponds to the discriminator part. So that's the which is a simple representation of, I think so. I have put it in the text. You can think of it as a simple discriminator, which we have referred to earlier, which
Okay.
from
And
the
what
text,
is
yeah.
sorry, what is PR in the second term on the second line? There's expectation over X drawn from PR. What is PR?
This is the probability over the R, the small r here is the, I think so,
Random, right?
the values, yeah.
I think that's where you're using like feeding the random stuff to the late as a latent variable to generate.
Mm-hmm.
So random noise from a Gaussian then, or?
Yeah, I think that's what that PR is.
And then finally, there's the X. The third term has X drawn from P of X hat drawn from probability distribution of X hat. So what is the probability distribution of X hat?
That's just, I think so, the latent space, the probability distribution that we are taking in from the latent space. Uh, or X bar, the X tilde is the latent space. I'm a bit skeptical here. Since this discriminator, yeah, it's the other way around. X hat is the from the probability based distribution in the expectations of the latent space that you're trying to reach. X bar is the discriminator that we are trying to discriminate, and X is the original image, which some that there are three versions, no? Three versions to it. The original, the with the random noise that's being added, and the third is the how do I say it? The latent space interpolations, the vectors from the latent space. So in this paper, they haven't I think so defined these terms in a broad way. We have to refer to the original. This is taken from the WGAN GPs on regular. It is similar in many aspects to that.
So they're
And
drawing this notation from a paper from.
yes, from a different paper, which is the Wasserstein, the sliced Wasserstein distance. So
I see.
that's what the formulation is. Yeah.
I've heard of that. I just don't know what it, the Wasserstein GAN distance. I don't know what it means though.
It's a kind of symmetrical, like Jensen Shannon's. It's when we apply kind of one Dirichlet, I think so. If I'm not mistaken, if my memory serves me right, there's a cool paper with respect to that too. It's a kind of a distance where this, if I have just opened the
well,
paper,
as you
it's
said,
all
the Shannon Jensen, the Jensen Shannon is distance is basically
symmetrical.
like
Yeah.
a distance between two distributions, right? And so that's what this is too. The Wasserstein distance is also some kind of a metric that tells you how close one distribution is to another.
Yes, it's the EM distance measures the cost of the optimal transport. As I just open up the paper, and instead of just measuring the normal distance, they are measuring the mass of how much the cost is transferred, because it's the infimum or the the product over all those joint distributions. So intuitively, it indicates how much mass must be transported from X to Y in order to transform the distributions PR into the distributions P of G. That's the R and the G that we have referred to here. These two guys here.
Okay.
And here.
Which document is this? Is this another slide presentation
Yes.
for the paper, but this is a really long one. It has 77 slides, whereas the one we were looking at had only 13 slides.
Yes, this is a whole how do I say it, end-to-end uh, formulation of the uh, things that this research paper is based on. So they have used many of the, let's say, uh, uh, techniques that were built on the earlier papers. And here I've shared a WGAN uh, research paper in which they have formulated this Earth movers distance with respect to the PR and PG. So they have taken this equation from there and then sliced it up. So they have made their own contributions on top of it. And that too, I was referring to, it's based on a 2017 paper. So this is a combination of all the things that have happened up until this point, and they have included it all.
Oh, so this paper, this 2017 paper is a very good, you're saying it's a really good summary of everything about GANs that happened up to 2017.
Yeah, this the WGAN GP, the Wasserstein GAN paper that I've just shared is the formulation is the original formulation of how Earth movers distance came into play, and what was the difference between the Kullback Leblers, the Jensen Shannons, and the Wassersteins. And they have in this and what the WGAN's GP wears and how have they improved it further uh, in this research formulation to improve that cost function. So it's how do I say it, spin over this. And in the second page of this program paper, they have listed as that they have used a Wasserstein distance from two papers in 2017 uh, by two guys there. And uh, so there you can get a formulation on how these things came into play.
Yeah, thanks. And this paper looks long. It looks 32 pages, but really it's only like about 16 pages of main text, and then the rest of it is appendixes and pictures and stuff.
So moving forward, so this is the expectations over, as I alluded to earlier, and then this guy has to surf on those waves and reach that test, that treasure test, that's the convergence that we need to have. What happens in the higher resolutions? That's the latent space that has the generator that is fed into the 4x4, and we get a 64x64 generated images, and the discriminator adds uh, some sort of a noise here before being fed. The generator adds some sort of a noise, and then the discriminator classifies it as real or fake. But we are not doing this here. Uh, there are ways everywhere where to show. There it is. So there is some sort of a skip connection also being added here that we refer to as the in naive terms it can be called the concatenation, but it's the linear interpolation. I'm using that word right.
You're talking about nearest neighbor interpolation to get up from 4x4 up to 8x8. Yeah, nearest neighbor interpolation is how they do it.
Nearest neighbor with respect to the alpha increase from uh, 1 minus alpha, from the 16 cross 16 layer, and the alpha from the 32 cross 32, which is being multiplied. So that was that. Then They have the generators, they have this replicator blocks, the nearest neighbor upsampling techniques, and the 3x3 convolutions that they have used. Firstly, they have converted this to RGB, then and the next block, they have used the upsampling 2x and then 2 RGB, and then that's the linear crossfade that I was referring to earlier. This from this to this, which you showed in the previous presentation. It's just a visual. How do I say it? They have used a PNG here, and it is a bit intuitive. And this,
It's kind of the
oh,
it's the mirror image from the left hand side. The right hand side is the mirror image of the left hand side.
yeah,
The reverse transformations.
yeah, the reverse transformations here. And there must be a video here. Then we have just wanted to. This is the variation with respect to. I think they are trying to uh, uh, formulate this as some sort of a divergence problem uh, in which they are trying to uh, get this discriminator to a latent space. This is the first time. This is the mini batch discrimination. Yes, this is from a different paper here. Mini batch discrimination, in which they in each batch update they add some sort of summation if we look at it, and then they perform the concatenation from the intermediate features, and then the results go on to the next discriminator. So that's the step here with respect to the mini batch discrimination. And that's the slide that you were explaining in the earlier stages, in the latter stages, with respect to the MB standard deviation that is being put in here. That's the pass through with respect to the each mini batches that go at each, how do I say it, each block of this, and then they are concatenated. This is this was the main figure that I wanted to show with respect to the standard deviation over the images, how they work with respect to the normalization techniques that they have used.
So in the second series of pictures in the second row actually, and it has those three pictures in a row, second from the top, right? You have those three, and then the next row has those. It's right underneath the brown line. Yeah, that one. So that one is the one we talked about, right? The where you take each, you normalize, you divide by, you take each vector across the filters and then normalize it by its length. And then that's what you get.
This is not pixel-wise normalization, right? This is mini batch standard deviation that they are adding in, so that we're talking of two different ideas here.
Okay.
This one is basically like it says that if what is being fed into D has a smaller standard deviation, that means all the images look alike, so you're going into mode collapse. Whereas if you have those three images which look very different, that means your standard deviation is going to be higher. So that means you're safe from mode collapse. So this is just a technique to prevent you from getting into mode collapse. And from what I understand is that you just take the standard deviation. Standard deviation directly tells you whether the images look alike or don't look alike. And you just stack that onto, after you take the average, you kind of average all those pixels, you just get one scalar. And all you're doing is just, if you had like 4x4 by 512 channels, you append this behind that. So it becomes 4x4 by 513 channels now. So at least that's what, like this, as far as I know, has nothing to do with the pixel-wise normalization that we saw, right?
It does though, in the sense that you're going across the filters, right? I mean, if you look at say if you have 3 filters and then you look at the same pixel in all 3 filters, the same pixel position, if that pixel is close in all 3 of those filters, then the standard deviation is very small for that pixel.
Even if that, yeah, I mean, I see the analogy that you're drawing, but you see the last part of the figure in this, it ends with there's one scalar written over there, right? You don't do that in pixel-wise normalization. Wherever Mayank had drawn that circle, the figure below that basically says averages over the features, and then you take an average over the pixels, which just gives you a single number. In pixel-wise normalization, you get a single number across the channels, and then you divide each and every pixel in that X and Y position by that constant.
Yeah.
Here, you're just appending a new scalar altogether, which tells you how much variation is there in the images that are being fed to your discriminator. Actually, if you go back to the text in the, that section explains this very well along with the figure that Mayank is showing.
But why in this figure, why are there 3 sets of images?
But that's just an example. How many over, whatever your batch size is, that's going to be produced at each instance.
Oh, okay. So you're averaging over a batch.
Right. That's why it's called MB standard deviation, right? So it's a mini batch standard deviation.
Okay, got it.
So I think page number 602, where you have mini batch standard deviation, and if you look at the formula there, that kind of fills in very well with this picture. You have a TF concat, that's what you see in the last stage. We had only 3 channels, it became 4 channels. And what you're concatenating is the inputs, which again correlates to this. You initially had those 3 feature maps, those same 3 feature maps are there down. And you're concatenating it with tf.fill, batch size, comma, height, comma, width. And whatever you're filling it with is that V, and that V is that one scalar, which was.
Okay, so that's just one constant filled into all the pixels in one of the feature maps. Okay.
Yep.
Okay.
So the last sentence on that basically says, thanks to this layer, the discriminator will have will have easy access to this statistic, making it less likely to be fooled by a generator that produces too little diversity. This will encourage the generator to produce more diverse outputs, reducing the risk of mode collapse.
So what happens if that appended new feature is small? How does that encourage the network to make it bigger? What's the feedback mode? I mean,
let's see what else.
That will, I think so, depend upon the cost function that we have. All right. So this can be a huge 2-hour presentation in itself too. And recently just came across this today only.
So in some way, this extra feature that you add on, if it happens to have a small standard deviation, you know, that if that feature map has small numbers in it, then somehow that encourages the network to do something else so that in the next batch it's bigger.
Yeah.
That's what you were saying, right, Rekil?
Yeah, so that's what it says, making it less likely to be fooled by the generator that produces too little diversity.
Okay, so I understand what they're saying, but I don't understand the mechanism.
I agree with you. Yeah, I don't know the exact mechanics. I can't say if this goes down, that should go up, sort of a thing. I'm trying to draw that, but yeah, I can't. Yeah. I don't have a clear picture of that either.
Okay.
I think so, yeah. In the paper on in the program paper on page number 5, they have uh, 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 mentioned the multi-scale statistical similarity and how those upper images map to the Wasserstein distance, the SWD metric that they have taken here, and they combine over the average pixels. Yeah, even I will have to go a bit
when
into
you say
detail.
program paper, which paper do you mean?
The program, the
The
original paper
program.
on which,
I see.
yeah,
Yes, yes,
the
yes.
progressive growing of GANs,
Yes. Okay.
paper on which this presentation is based on.
Yep. Okay.
Yeah, even I will have to
Program.
look
You say
into it.
page
Yeah,
5. You said page 5
yeah,
on that paper. Okay.
yeah.
Okay. Page 5, because I have it open.
Increasing the variance and
Multi-scale statistical similarity. Is that what you mean? That section?
yes, that section, which is respect to the number of if the earlier section, the 4.2, you had the number of pixel wise feature vector normalization. That's the second part on the bottom. That's the average over other pixels, and the average over features. That refers to uh, refers to it's here somewhere.
Joseph and Raquel, here's a thought as to how this particular scalar might help the network learn. Isn't it the case that if this scalar were smaller, then whereas the discriminator will learn that when the real images are given to it, it gets a value which is much larger. Whereas if the generator continues to produce images which are real but which are only of certain modes, then this scalar will continue to only have smaller number of range of values than what it sees from the real images. So wouldn't that encourage the discriminator to then predict that these aren't real because you're generating smaller range?
That sounds quite reasonable.
You see what I'm saying?
Yes.
That's how this feature will help the generator, the discriminator to learn that the range of the generator is not sufficient to match the range of the real images.
So this is an example of what I guess Jeremy calls helping the network by
Learning.
sort of engineering extra features in there that make the job easier.
Right, to learn.
Yeah, that's a really great insight, Srinivas. I think that's right.
Yep, agree. And then they let's wrap this up. What they have done with respect to the pixel norm. Okay. This after the leaky RELU with respect to the weights and biases, they have added this. And I do not understand this. What they are doing here with respect to the alpha one. Okay, that's the alpha and the beta. With respect to the pixel-wise feature vector normalization that those vectors that are being added. That's the visual representation of that. These are the in the upper. Yeah, this is the unnormalized and this is the normalized form.
Yeah, that's the one we were discussing. That's the one we were
Yeah.
trying to draw when I was drawing those horrible pictures. But this is a better way of, yeah, this is better.
Yeah. So that's the pixel now.
Yep. Yeah, that's exactly what we were going over before. Yeah, how A gets mapped into B.
Yeah. This is the formula, yeah, that we had discussed with alpha x comma y over root of 1 by n from and the summation j0 to n minus 1 and that.
Yep, that's the normalized part. Yeah.
Yeah. And then just look at the results. What we have done. Slice versus time, equalize running rate. So this is the sliced versus time distance. Now it affects. And this is the interpretation of that with respect to the visual.
So A is at the left and B is at the right. I'm not sure what this
Yeah,
represents.
that's the with respect to the versatile distance. What's the difference between the versatile distance? I think so, and the general KL or the JS divergence that we can get. That's the total. What's the difference between the images that can be generated from them as opposed to using the versatile
Right,
distance?
right. So the Wasserstein distance is calculated from the downsampled images, right? The original images are whatever 1024 by 1024, but the images that are
Yep.
used to calculate the Wasserstein distance are just 4 by 4.
Yeah, it seems like it. Yeah, four by four. Yeah. If we have not scaled it up,
What's happening across from left to right in this diagram where the initial image gets blurred out?
that's the convolutions that are being applied. I think so. Yeah, that's
Okay. So
yeah.
those are the feature maps that are generated by the convolutions.
Yeah.
Okay.
You can see that feature maps here. This is the the FI distance and how they have equalized. And that's the alpha parameter, the equalized learning rate with respect to those MBSTD and those blocks that we have talked about. These four blocks and how they are in a naive sense concatenating here. What's the signal to noise? That's it. And then the con 2D, the network is passed to the con 2D, and then the biases are being added here. So that's the way that we get from the C. That's the C. I think so with respect to the parameter that we had in the C is the per layer normalization constant from the He's initializer. So yeah, they have taken the He's initializer and they have the Wi hat is equals to Wi by C, where Wi is the weights and the C is the per layer normalization constant. And why they're doing this is because this dynamically instead of during the initialization is the scale invariance that is used in the adaptive stochastic gradient descent like RMS pop and Adam. So just to formulate to convert this optimization problem as a that so they such that it converges. I think so enough. The reason that they have given is scenario. This is the scenario modern initializers cause, and thus it is possible that the learning rate is both too large and too small at the same time. And since it is a dynamic approach, and then the learning speed is same for all the weights. So that's the reason that they have given. Then this is this cross. This cross, I think, so refers to the cross product which they are doing with respect to adding the C parameter, approximations from
Just
the
like
weights to.
it's just like element by element multiplication.
Yeah,
Is that,
yeah,
is that what that is?
I think so. That's it.
Okay.
And then, so that's this part. Then this is the progressive growing of how the 1+1 convolutions with the match resolution uh, linearly crossfades into this interpretation. So that's the whole thing that is being coming together. The 3-4 concepts that we had discussed earlier. That guy. And this is the generator, and then this from the discriminator. It's just the reverse. This is how the flow of the data. You can visualize it according to that. This is the whole end-to-end diagram. I think so. And then yeah, that this is it.
So the left side was the generator and the right side was the discriminator on that last spot.
Yep.
Okay.
This I particularly found interesting because this kind of presentation, which they have taken all the things into account with the smallest detail with respect to the cost function and the features that they have added. This was really how do I say it, a seminal work. I think so.
So
And
if
then
you read that that PowerPoint drawing that has the PowerPoint document with the 77 slides, that basically explains the whole paper that way, the whole paper that we looked at, right?
Yeah, even if you go through the whole paper, you won't be able to get to all the concepts unless you browse through the how do I say it, the those citations that they have mentioned. So this is a complete representation of everything that came across to perform the progressive growth of grants. Then and then the next section is the style GANs. That's if we since we have already understood this, so that will be easier. I think so.
Well, I read the StyleGAN section and did not make much of it. You know, it's I could understand pieces of the drawing, but that figure, figure 20, page 605, from the text, I could not understand how that works. So it looks like if I want to understand it, I should look at the paper.
Yeah, since they here also they have taken the Wasserstein distance from the mapping network. So since this is the mapping network, adaptive instance normalizations. Okay.
These were the pieces that I kind of figured out. Z is basically a random vector that you pull out, noise, random noise. So let's say something like 512 dimensions. You pass it through this multi-layer perceptron, which is a bunch of fully connected layers. And you basically again end up with W, which is again another 512 vector of noise. So what this MLP basically is doing over there is it's kind of helping you disentangle stuff. Otherwise, everything is too entangled. And what that basically means is if you want to try to control a certain feature, let's say, for example, you just want to change the hair, or you just want to change the color of the, I don't know, your shirt or something. If you just start with Z, it's like when you draw the MLP, you see that each neuron is connected to all the other neurons in the next layer, right? And that's what the entanglement is. So this basically helps in reducing that entanglement. So that's why you map from Z to W. And then W is basically—
And generally, like W would be smaller than Z, right? Or is that not
no,
true?
in this case, if I'm not wrong, it's the exact same size. It's just 512. That's what.
So
the
it's like
function
an
is.
it's like an autoencoder then? That
Yeah, pretty much. Yeah, in this case, yeah. I actually don't know what the in-between FCs are. I don't know if they kind of like funnel down and then funnel back up, or they pretty much
Yeah,
are
it
the
doesn't
same
say.
size. But yeah, the main thing is that it kind of helps you disentangle stuff, and that's the key thing. Like when you see the progressive GAN, I mean, any of the style GAN videos or the stuff that you were sharing, they kind of give you knobs where you can change this certain thing up and down, and then you'll see like a person having glasses or not having glasses, or a person becoming the opposite gender and stuff like that. Basically, that this kind of helps you with that. The W, which was just a 512 noise vector, basically fed as input back into this for the adaptive instance normalization. And the adaptive instance normalization is basically instance norm. And like instance norm, like pixel-wise normalization is pretty much the same thing. It's just across different axes. It's across the, I think across a channel and for each instance. For each channel and each instance, that's what that is doing. So it's just one form of normalization. And the reason why you kind of use instance norm here is at the end of the day, you're going to generate like one image. So that's why it's like instance. And if you kind of draw parallel, if you remember neural style transfers, there also instance norm is what is used. And there again, it's the same use case. You're kind of trying to generate an instance. So that's why I think instance norm makes sense. And that's why it was used. The adaptive part comes from W is basically taken and you calculate its, I think, mean and standard deviation. And so you take that mean and standard deviation, multiply it by whatever comes down from the upper conv layer. And that is what is kind of fed into this adaptive instance norm. So those were the pieces that, yeah, I figured out.
So
Yeah.
so the A's are these, he talks about the A's as being something like features like freckles or glasses or something like
Correct.
that. Those are the knobs that you were talking about that you can twiddle.
Right. That's
But
what they talk about, that when you add it here, like at every layer, what it does is, obviously when it goes from 4x4 to all the way to 1024 by 1024, the 4x4 region and lower down there basically controls the coarse features. Whereas as you go to the 1024 side, that is controlling more of the fine-grained features. And I think on the paper Mayank is sharing, there is one diagram which basically has an interpolation between like W1 and W2. So you can use like two weight vectors instead of W. And W1 and W2, let us say W1 gave you certain images, W2 gave you certain images. If you used only W1 for the top half and W2 for the bottom half of the network, you would basically generate that last figure. Can you pull down just that last one that you just showed right now? Yeah, sorry, the one about that. Yeah, this one actually kind of shows you the course detail. Yeah, figure 5 basically shows what, if you change, if you look at the first figure top left corner, A basically shows as you control like the finer details, you can see the curls there, and the eyelashes, I'm sorry, eyebrows are also more finessed. Whereas on the right-hand side of that same figure, you see that is playing around with the coarse layers, you kind of change more on the underlying structure. So that is what that, can you go up, Mike, there's one more figure there. I think it
Yep.
was.
So,
Yeah, that one itself.
this is the feature code, uncode.
Below that, figure 3, I think.
Yeah.
Yeah, so that's what you can see, that source A, source B. So source B and source A are these initial images, imagine, and that in between grid that is generated is basically talking about what happens when you use like the lower end of the network. That is where the course style changes. And that's why you see that if you look at the first row, all you're trying to generate is that lady is kind of there, but then you're mixing it up with the course level features of the man. So the specs is coming in, all that kind of, the child is also being shown with that lady's features. That sort of mixing is happening. But as you go to the bottom one, the fine detail, you see that the fine detail, the lady really doesn't change. It's only the fine details like the hair color and stuff like that is changing. So yeah, that pretty much I figured out. I think, yeah, that's, let me see if there was one more thing.
So what's inside the A boxes?
The A?
Yeah, the A, the different knobs, the on the
So
small
A
little
is
boxes.
again, so it's coming from W.
Mhm.
So W is just the noise. Just hold on there, Mayank. So if you see equation 1 over there, all it's doing is it's doing xi minus mu xi divided by sigma xi. That is nothing but instance norm. And the adaptive part there that is coming is the y, which is coming from W. The y, I can't, what exactly is that? The scale and the mean that you're seeing over there, that is being multiplied and added.
Yeah, that's
That
kind of like the batch.
y,
That's
I-
kind of like batch norm that where you take
Yeah, that's
the,
all. That's what I was saying. It's just along different axes. That's all that is doing.
it's like the gamma and the what is it? The gamma and the beta from batch
Yeah.
norm, the scale and the offset.
Yes, but here the adaptive part of it is basically talking about the style. That's how the style changes. Going back to A, that is what he says here. A stands for that learned affine transform, and the mapping network F consists of 8 layers. Blah 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 blah. Where is that? Hang on, I have this.
So, which respects to A, quality and style base.
So A, if I'm not wrong, is the one which is just calculating that YSI and that YBI,
Okay.
the style and the bias.
Okay, and
I'm
then
sorry,
the
scale and the bias.
right, and then on the left hand side, the stack of fully connected layers. What I read in there is that there are no activation functions, so these are just affine transformations. So why
Is
doesn't-
that, sorry, is that the MLP? I don't think that's the MLP. That's the next part. That's the A, right?
No, I think the stack of fully connected layers, the one on the left, he says that these are affine transformations. I think he says that.
I read that and I thought that was.
No, I read that.
An 8-layer MLP that maps the latent
Entanglement studies.
to the vector W.
So
So MLP, right? It says this vector is then sent through multiple affine transformations. That is the A, right? So the MLP.
the A is the affine transformation. Is that what you're
right,
saying?
right. So the MLP still has activations. I mean, the activation function still exists.
Okay, yeah, that would explain that, because otherwise I don't see why you would need
Yeah,
8
there's no
layers if you
point.
just
Exactly.
replace it with one.
No point of having that.
Yeah. Okay, I understand. And then, so on the left-hand side, you have the A. On the right-hand side, you have noise going into B. And again, I'm not sure what exactly B is.
Yeah, I forgot what that is.
They should have. ये है ना? Yeah. Yep. Here A stands for the learned. I think so. If you can see the affine transformation, and B applies learned per channel scaling factors to the noise inputs.
Okay. Okay, so the affine transform has a scaling factor and an offset, but the B only has a scaling factor, I guess.
Yep.
Okay.
With respect to, since they are scaling it from 4x4 to 1024 cross to 10224, so that's the difference. Since it consists of the 8 layers, so that's the range that they are.
Okay.
So nowadays, I think so that this has been extended to StyleGAN 2 and style flows with respect to the flow-based uh, auto that stuff, auto regressive, uh, uh, but it's costly. Cost, uh, uh, but yeah, that's the state of the art right now with respect to those fine-grained in turning the knobs, and that's the A part here. And they can do it in a pretty fine-grained manner with respect to every hair of uh, human can be how do I say it? That can be added or removed from the image in a much how do I say it? Uh, uh, that has a much greater visual fidelity. But that's of course it's costly, and that kind of interpolations have also been built up into a couple of uh, uh, softwares that have been released to the public too. So we can set up our code, and if we want to do that kind of modeling, or uh, we want to set up our own photo studio, then we can do that too.
Yeah, but it seems like you need an awful lot of processing power, because remember that video that we looked at, he was talking about, they were showing like time lapses of this is after it trains for a week. And you're wondering like which machines is it training on? Is it just training on a laptop, or is it training on a cluster, or is it training on a whole bunch of GPUs together? I don't know how much compute power you need to actually play with those style GANs.
This requires a whole lot of compute power. And a couple of papers that I've read, and the authors that I've talked to, and they referred to as they were using a DGX box that comprised of 8 V100s.
Jeez. Okay.
Yeah.
Okay.
And
8 V100s and
8 V100s,
yeah.
16 cross 8 times the VRAMs that they required.
And with such a compute infrastructure, how long does it take to train a model again on
yeah,
1024 by 1024?
I think so. It depends upon the resolution that they took,
Yeah.
from 3 days to a week, and a couple of weeks too in some cases if they try to increase it. And then
Well, I guess if you wanted to play with it on your own machine, you could try to scale things down, like just instead of trying to make 1024 by 1024, you could be content with 128 by 128, or even smaller, 64 by 64, and see what happens.
Yep. And we can also try to have some sort of a different instance normalization on that. But I think so. They have tried every possible combination that exists, uh, because that sort of compute and the experiments that they do regularly, they only publish the experiments which are the how do I say, the leading,
Successful.
yeah, which has the most successful part of it. And sometimes it also depends upon first they try on the experiments, see what works, and then they go and write the architecture and the paper that corresponds to the successful uh, representation. So that's and in the style flow, the paper that I recently came across, what they're doing is they are using the generator of the style guide too, and for interpretation, for the how do I say it, for the inference part, they are trying and adding their own uh, differential blocks of formulations. I think they had four or six that the injective. Uh, I quickly open the paper up.
Maybe you can post the StyleGAN2 and the style flow paper that you're talking about on
Yes.
on the Slack.
Yep.
Okay.
This is the style GAN
Thank
2. And let me quickly flow. I was just reading it yesterday and I found it. This is it. If you can just, see my screen.
Yeah. Yeah.
Yeah, this is the reverse inference and the forward inference that they are doing. Yeah. These are the CNF function blocks, which is the main.
CNF,
Yeah.
conditional normalized flow. Is that what that is?
Yes, I think so. That's what it is. Normalizing flow. Conditional continuous flow. Continuous normalizing flows.
Conditional continuous normalizing flows. Okay.
Yes. And this work was done with Adobe. I think so. Adobe in mind. So StyleGAN and StyleGAN 2 is with NVIDIA, and this is with Adobe.
What's the
How do,
difference between StyleGAN, or just briefly, the difference between StyleGAN and StyleGAN2?
yeah, there are a couple of differences. They have that's the here the architecture. If uh, here, if we can see that's on the left, A and B is the style GAN, and the C and D is the style GAN 2. So,
Okay.
yeah, these are. So, wait, yeah, the original style GAN learned A, that's the affine transformation, from the W that produces a style, and B is the noise broadcast option. And here, what they have made changes to the architecture in the style GAN 2. They have removed some redundant operations at the beginning and moved B to the outside of the active area of style, such that they can only adjust the standard deviation per feature map here. If you, that's the revised architecture. So from inside, they have moved it outside here. Yes. So what this does is, here, that's the couple of changes that they have done. They replace the instance normalization with a demodulation operation here. Demod instance normalization. So the second or the first set of images that we referred to in the program smart, First was the mini patches normalization. The second was the pixels. So they have replaced let's say the instance normalization with the demodulation, and how this affects. I still have to get into the details, but yeah, that's the highlight of the changes that they have done. Yeah.
Mhm.
So that's the latest state of the art. Going through it.
And do they show some of the results and the images in that
Yes,
paper?
I think so. So, yeah, and that's the replacing the normalization with the demodulation removes the characteristic artifacts from the images and activations. So on the left, I think so. Yeah, is the artifacts that are there, which has been removed. You can see the images between the leftmost, the middle, and the right one.
Mhm.
Uh, that's the figure 3. And in the figure 5, they have given a distribution of the PPL scores of the baselines. As we can see, this is a kind of a clipping that is being done here with respect to the difference between the style GAN and the style GAN 2, the architectural changes that they have made. This is the PPL distribution that has been improved considerably because we want it to be sampled from a particular peak. So the variance is reduced here, perceptual path length, and this uh, improve the smoothness of the images. Then they have compared the generators, the MSG GANs, the input-output skips, and the residual nets, and how they affect the how do I say the bilinear up and down sampling with respect to those convolutions. And then the images. Then that's the style GAN generated images. These are the style GAN 2 images which are generated in the middle. And these are the real images. And they worked on the L SUN car and the FFHQ datasets too here. Yeah, the next part there. These are the handpicked results. Of course, they are biased, but because they pick only the best. But you can we can also set it up and play around with it. This is the FFHQ dataset, the Elson car, Elson cat, church, and the horse. The, and the various hyperparameters that they have used. These are the feature maps. Of what they represented. Mm, that's simply being they give a example as to the normalization of the viewable dynamic range that uses the instance normalization. This is for the style cam, and I think so. The progressive growing also comes into effect here. which we have seen in the earlier paper. So that's why that was seminal, because they have used the methodologies, the tricks that they learned there in the StyleGAN version 1 and at 2.2. And this is the regularization and the derivation of the pointwise Jacobians.
This is the StyleGAN 2 paper that you're looking through?
Yeah. This is the StyleGAN 2 paper that you're looking at. I'm just giving an overview of what this spectral normalization and other things that have an effect on.
So what year is the StyleGAN 2 paper?
I think so. That's the same year. Yeah.
Is it last year? Oh, it's 2017 still?
No, this is, I think so. This came around and
2020. Okay, so this is last year. Yeah.
And this is the 8 GPU DGX1 that I was talking about.
Yeah.
So that's what I alluded to earlier. They experimented with all the things and came up with the how do I say, the best representation of what is the best normalization. I think so. The effects of the spectral normalization, they experimented with it and they concluded that without spectral normalization, it gives a better result. So if you think about it, how many experiments and how much power would that
Yeah,
have?
they actually looks like they had they actually kept a table, they kept track of it, so they could predict how much, they could tell you how much power they used in the exploration phase and then in the final phase and so on.
Yeah. Energy consumption.
Yeah. Okay, good place to stop. All right, and then we'll get together on Sunday to start the reinforcement learning, right? And you're going to lead that part.
Yep.
All right.
All right. So goodbye. Take care. Thanks, guys.
Thanks, Mayank.